Welcome to Global Virtual School students. This is your first year chemistry class. I am Dr. Jalbano, and today we are discussing topic the hybridization of atomic orbitals from chapter 3. Chapter 3 is the theories of covalent bonding. Basically, theories of covalent bonding include Valence bond theory we have discussed in previous lecture, and hybridization of atomic orbital and molecular orbital theory, and molecular orbital theory will be discussed in next lectures. And in hybridization of atomic orbitals, basically all of three types, that is sp3, sp2 and sp. So in this we will discuss only sp3, and we will implement this different postulates and concept with the reference of different examples. Students, after completing this completely hybridization topic, you will be able to understand or explain the tetravalency of carbon, because carbon is tetravalent, it forms 4 bonds, and trivalency of boron can form 3 bonds, and the beryllium divalency, so how the beryllium form 2 bonds. This will be explained with the help of concept of hybridization. Students, why this concept we need to bring this hybridization concept? Basically, Valence bond theory, in previous lectures you have learned that partially filled atomic orbitals decide the number of bonds. If partially filled atomic orbital is 1, then a single bond is formed. If partially filled atomic orbitals are 2, then 2 bonds are formed. If it is 3, then 3 bonds are formed. So Valence number, so that 1 partially filled or 0 or 2, 3, 4 is related to the partially filled atomic orbitals. So if atom has no partially filled, so its valency will be 0, like beryllium. Beryllium's atomic number is 4, and its electronic configuration is like 1s2, 2s2. It has no partially filled atomic orbitals, so it has 0. 0 means it cannot form bond with any, and it will be neutral. Similarly, boron, its atomic number is 5. So according to its electronic configuration, 1s2, 2s2 and 2p1, it has 1 partially filled, so its valency will be 1. It should form 1 bond. It should be a monovalent. Similarly, carbon, its atomic number is 6. So 1s2, 2s2 and 2px, 2py and 2pz, 4, 5 and 6. It has 2 partially filled, so it should be a divalent. But you have learned in previous theories, valence electron pair repulsion theory, that beryllium is divalent. We have the example like beryllium chloride, it formed 2 bonds. Then how it formed 2 bonds? Why it is divalent? It should be neutral. Boron, you have learned the example BF3 or BCl3. In this case, boron is trivalent, but according to this, it should have monovalency. It should form only 1 bond, but in most of the compounds, boron form the 3 bonds. Similarly, carbon should form 2 bonds, but most of the time, like CH4, it has 4 bonds, CCl4. And most of the organic compounds where carbon is important atom of the organic compound, it form 4 bonds. Most of the time carbon form 4 bonds. So its divalency, trivalency and tetravalency can only be explained with the help of concept of hybridization. So what is this hybridization, and who bring this concept? Pauling and Slater resolved the Valence issue and introduced the concept of hybridization. And so what is the hybridization? Hybridization, students, basically is a process. This is a process of intermixing of atomic orbitals of different energy and different shapes. So orbitals that are in different energy and that are different in their shapes, they intermix to form new orbitals of same energy and same shape. This process is called hybridization, and the orbitals that are formed after their mixing, they are called hybrid orbitals. And what are the features or particulars of hybridization? Hybridization basically involves mixing of pure S and P can be 1, 2 or 3 orbitals of an atom to form new hybrid orbitals. And the number of hybridized orbitals, the orbitals that are formed after mixing, that number is equal to the number of atomic orbitals that are overlapped. So if you have 2 atomic orbitals, so 2 hybrid orbitals will form. If you have 3, then 3 hybrid orbitals will form. If you have 4 atomic orbitals that overlap, they will form a 4 hybrid orbitals. And after hybridization, the bonding process takes place. So bonding do not start before hybridization. So when hybridization is completed, then bond formation process takes place. And a bond process occurs by overlapping of hybrid atomic orbitals. So now in this case, in valence bond theory, you learned that atomic orbitals overlap, but hybridization, hybrid atomic orbitals, they overlap, or one atom with a pure or hybrid. So hybrid can overlap with hybrid, and hybrid can overlap with non-hybrid, or you can say pure atomic orbitals, to form the bonds. In hybridization, energy required for excitation is compensated by energy released during the bond formation. So in some cases, we have to we consider that electron is excited from lower atomic orbitals to the higher atomic orbital, and the energy that need is compensated by the energy that is released during bond formation. So whenever bond is formed, energy is released. Whenever excitation is required, energy is required. So initially we have to give the energy to start a reaction, but as a process itself is releasing energy, so where energy is required, it consumes the energy released during the process. So now come to what is the Sp3. As soon as you know, Sp3 mean, in this case, 1s and 3p, like this. They intermix to form Sp3. So total 4 atomic orbital intermix, and total 4 Sp3 orbitals will form. Like the process of mixing 1 s orbital and 3p orbitals to form 4 new hybrid orbitals, Sp3 hybrid orbital. This process is called Sp3 hybridization. So we have different examples of Sp3 hybridization, like methane, carbon tetrachloride, ethane, ammonia and water. Now let's see how tetravalency of carbon is explained with the help of hybridization. First of all, write the ground state electronic configuration of carbon. Atomic number of carbon is 6, and its configuration is 1s2, 2s2, 2px, 2py and 2pz. px1 and py1 and pz has 0. It has no electron. And you know, this is the valence shell, and the shape of S, you know, is spherical. It contains 2 electrons. Px, like you say like this, it has 1 electron, and Py, like this shape, it also has 1 electron, and Pz is like on y-axis, and Pz has 0 electron. It has no electron. So now we consider that one of the electron from 2s is excited to the Pz. Like its excited state electronic configuration will be like one will left here and one will move to the Pz. So this will now contain 2s will contain 1, and all will contain like 1 electron, Px and Py also, and Pz also. So now you can see that these are now 4 partially filled. So carbon will form 4 bonds. But as we know, in CH4 our bond angles and lengths are equal. But in this case, S has spherical shape, P has dumbbell shape, and they are on different axes. So this explained with the help of hybridization. Now we consider this one S and these P. They intermix to form hybrid orbitals that contains S character as well as some P character, and they will be like this. Now this will be called now Sp3. This is not a pure S, not a pure P. So this is a sp3, 4 intermix and 4 will be sp3 new hybrid orbitals will be formed. They can be at any angle sp3 and all contains 1 electron. So on carbon there will be not sp, x, py, pz, but now carbon will contain sp3, this one. Now this one, now I'm just ignoring the smaller lobe for convenience of to draw the shape of the methane. Now and this sp3 is like this one sp3. Now this sp3 is like this one sp3. All have this 1 electron in each, and now this fourth one is out of plane, so this is drawn like here sp3 and it has 1 electron. So now these are all orbitals are sp3, sp3, sp3 and sp3. And for hydrogen, you know it is 1s1. So for hydrogen, one will come here and will form a bond. This will be sp3s. Other hydrogen, second one will come here and a paired spin and sp3s sigma bond. So third one will come here and will form, this is sp3s, because this is s from hydrogen and sp3 is from carbon, and also will come here s from hydrogen and it has a paired spin, it will form sp3s. So total are 4 sigma bonds by the overlapping of sp3s, and geometry will be tetrahedron. And angle will be between them, like this is the carbon and this one hydrogen. All angle will be 109.5 degree, and at regular tetrahedron angle is 109.5. So whenever you have to ask to draw the geometry of the geometry of the methane on the base of hybridization, so first tell them which type of hybridization. So in this case it is sp3. What is the geometry? It's tetrahedron. How many bonds and types of bond? That are 4 sigma bonds and all are sp3s. And in this case the geometry angle is 109.5. So look here, this tetrahedral shape for what? Methane. This is the carbon, this is hydrogen, 4 hydrogen, and these all these are this one. All are sp3s sigma bond. So total 1, 2, 3, 4. This is also a type to how to draw the shape of the methane. These are different types to draw the shape of. This is the tetrahedron, regular tetrahedron, and angle is 10. All angles are 109.5 degree. Let's see this animation.
A carbon atom has 4 valence electrons. 2 of them are paired and located in the 2s orbital, but the other 2 are unpaired, occupying 2 of the 3 available 2p orbitals. When during reaction one s electron is excited to a p orbital, there are 4 unpaired electrons available to form covalent bonds. The single 2s and 3 2p orbitals hybridize to give 4 equivalent 2sp3 hybrid orbitals. Overlapping of the hybrid sp3 orbitals with the s orbitals of 4 hydrogen atoms produces 4 sigma bonds. The resulting methane molecule has a tetrahedral geometry. The bond angles are 109.5 degrees. The shape of the molecule is in accordance with the experimental results and the predictions from the VSEPR model.
So that was for methane, and ethane is like 2 methanes are joined to each other, and between them instead of hydrogen Two hydrogens are removed and two carbons form the bond. They have the same ground state, excited state and hybrid state electronic configuration. So for this, first I will drawing for this carbon. This carbon contain sp3, sp3, sp3. So this is like sp3, sp3 and sp3. So this is sp3, 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 and fourth one is this one sp3. So in this case all contain one electron, so all will have one electron. And same for the other carbon, sp3, this is sp3, one electron, sp3, one electron, sp3, one electron, and sp3, one electron. This contains 3 hydrogens, so hydrogen with one electron will come here and will form sp3s, sigma bond. One hydrogen will come here and this will form sp3s sigma bond. Third hydrogen will come and this will form s from hydrogen, so sp3s sigma. For this case sp3s, because this is s from hydrogen, so here come again hydrogen sp3s, and also this sp, this one is sp3s sigma bonds, this sigma, and one will be formed between these two. This is sp3 sigma bond. So total are 7 sigma bond. One is sp3 sigma bond, this one, this one is sp3s, this one is sp3s, all are sp3s. Total are 6 sp3 sigma bond. So total bonds are 7 sigma bonds. Out of them 6 are sp3s and one is sp3 sigma bond. So this will be like this carbon. So this one, this will be like this one, hydrogen. So this one sp3 sigma bond, and all these are sp3s sigma bond, and this shape will be again a tetrahedron. Hybridization is sp3 tetrahedron, and bond angle is 109.5 degree. So this is like ethane. It is just like two methanes are attached and hydrogens are removed, and instead of the bond that is with hydrogen, now they have carbon-carbon single bond. So here is also carbon has tetravalency. So tetravalency can only be explained with the help of hybridization. No other theory explains the tetravalency of carbon. Now we have the example of ammonia, pH3, NF3, they all have the same. I will discuss only one. Nitrogen, its atomic number is 7, its ground state is like configuration 1s2, 2px1, 2py, 2pz. This will be like this, 2px. I'm just drawing 2px with one electron, this like 2py with one electron, and this is like 2pz with one electron. So they have 3 partially filled, but their angles are same. So this explained with the help of hybridization. So now we consider S and 3p. They intermix to form hybrid orbitals of 3 like sp3, sp3, sp3 and sp3. In this will contain double electrons, and this single electron, this will be single, and this will be. So 3 will have single and 1 will be completely filled. So this is nitrogen, like draw A1, this is one sp3 like this one, other is like this sp3, one is like sp3, and one also remain, 4 total sp3. Out of them, one sp3 is completely filled like this one, while other contains 1 electron in each, and hydrogen, that is 1s1 like this one, first hydrogen will come and will form sp3s sigma bond, this from S. other second hydrogen, this is from S hydrogen, and third, this will also form sp3 s sigma bond. This will form sp3 s sigma bond. So total are 3 sigma bonds that are sp3 s sigma bonds, and there is one lone pair, so that is not participating. But this lone pair bond pair repulsion reduces the angle, and its angle will be reduced from 109.5 to 107.5 degree, and the shape or geometry will be like pyramid, because at apex, one apex contains lone pair, and this angle reduces and it has a trigonal pyramid shape. So, and hybridization is sp3. So while drawing the geometry of the NH3, you have to mention type of hybridization, its shape, its angle, and the types of the bonds. Like this ammonia, nitrogen, one pyramid corner is occupied by lone pair, and due to lone pair repulsion, this angle reduces to 107.5. This is hydrogen, and the three corners are hydrogen, like this one, and this contains this lone pair, and this is to repulsion, this bond angle is 107.5 degree. Now we have the example of water or H2S. They are similar. I will discuss H2O. Oxygen atomic number is 8. Its ground state electronic configuration is like this. This is the valence shell. S spherical, like Px. This one is Py, and this one is Pz. In case this contains 2 electrons, it also has 2, it has 1, and it has 1. But the angles in water, they are like 104.5. bond lengths are same. So this explains the hyperhybridization. We consider that S and these 3p, they intermix to form hybrid orbitals like sp3. This is sp3, this is sp3, and this is also sp3. And out of them, 2 will have 2 lone pairs. This one lone pair and in this, and while 2 are partially filled, so it will form 2 bonds. This is oxygen. I will draw all the sp3. Like this is sp3, this is like sp3, this is like sp3, and this one is draw like this sp3. So out of them, 2 has completely filled, are 2 lone pairs, this one, and 2 have partially filled, 1 and 1 in this. So S from hydrogen, this is the S will come and form a bond. This is sp3 s sigma bond, here this one, and with this also hydrogen, this will form sp3s. So total are 2 sigma bonds that are due to sp3 s sigma bond overlapping. Okay, and then what is its geometry? It's bent due to 2 lone pairs repulsion. It has a bent shape. Bent shape or V shape or angular shape, and it has angle 104.5. angle reduces due to lone pair repulsion, that is strongest than lone pair bond pair repulsion, and then its hybridization is sp3. So these 4 things to mention while drawing the shape of the water, like is single bonds, types of bond, 2 sigma bonds, and those are due to sp3 s overlapping sigma bond. Shape, its shape is bent or geometrical or V shape, its angle 104.5, and then type of hybridization, this is the sp3 hybridization. So this is like water geometry. This is like tetrahedron, but 2 corners of tetrahedron, they are occupying the lone pair, and due to repulsion, this bond angle reduces and form a bent molecular geometry. And this is also like oxygen, hydrogen, and this is sp3s, and this is sp3s sigma bond, and this angle reduces 104.5. So I have repeated all the angles, lengths, geometries. So hopefully this will be clear for you. And now I am just comparing these tetrahedral. In case of molecule with no lone pairs, 0. It has tetrahedral shape. All these and bonds are 109.5 degree and lengths are same, and they have tetrahedron shape. While if it has one lone pair, due to lone pair bond variation, bond angle reduces 107.5, and these are sp3s, total 3 bonds, and in this case total 4 bonds. And due to 2 lone pairs, it has band shape, angle reduces further 104.5, and this is sp3s, and total are 2, and in this case sp3s total are 3, and in this case total are 4 sp3s sigma bond. So the things to mention, checklist is like, if these are the examples of sp3. So sp3 hybridization, tetrahedron, angles, and these types of bond. So hybridization is shape, its bonds, its angles. So also is sp3, its shape, its angle, and it's the type of bond. So you can be asked to how to compare the shapes of methane, ammonia, and water, or how to explain the tetravalency of the carbon. Some more questions are like, draw the shape of CCl4. CCl4 is exact like CH4, pH3 NF3 is exact like NH3, and H2S exact like H2O. So mention their type of hybridization, its geometry and angles, and also their bonds. So this was all about the atomic orbital hybridization, and out of that sp3 we have discussed with reference to different examples. Our next topic will be the continuity of the atomic orbital hybridization, and in that we will discuss the remaining two types, sp2 and sp hybridization.